In this video, I'm going to solve a projectile motion problem for an object launched on flat ground with a given initial velocity. And we're going to use the range equation to figure this problem out. So let's take a look. A soccer ball is kicked with an initial velocity of 22.5 meters per second at an angle of 40 degrees from the horizontal. Air resistance is negligible and g equals 9.81 meters per second. A is find the time it's in the air. B, find the maximum height of the soccer ball. C, find the horizontal range of the soccer ball. Now, in this problem, we're going to be using the range equation, and we're going to see how this makes things a lot easier for us. But let's start by sketching out a diagram of our soccer ball's motion. We launch at an angle of 40 degrees from the horizontal, and our initial velocity is equal to 22.5 meters per second. So we may have to resolve that into components in a little bit. But we're going to get a parabolic arc, something like this. And that's basically all that we're given. So let's label our diagram. Now there are kind of two important points here. In parts A and C, we need to find the time it's in the air and the horizontal range. So that's actually looking at the whole total motion. But in part B, we need to find the maximum height of the soccer ball. So that only refers to, basically we need to look at half of the motion in order to figure that out. So depending on which part we're doing, we're gonna basically be solving a different problem. For part B, our delta y is some unknown, and our delta x is half the horizontal distance. For parts A and C, our delta y is 0, and our delta x is just the total range. So let's just look at parts A and C first. Because this is an object launched horizontally, we can use the range equation to figure out our total distance. So let's find delta x total, which is going to be our red delta x, using the range equation. And that tells us that the range, that is delta x such that delta y is equal to 0, is equal to v naught squared sine of 2 theta divided by g. Since we already have the full initial velocity, we just plug in our numbers to get the total range. Our range then is going to be 22.5 squared times sine of 2 times 40 degrees divided by 9.81. I'm omitting units because they're in base SI. Our answer should come out in base SI. We can plug that into a calculator. 22.5 squared times sine of 80 divided by 9.81 gives us a range of 50.1 meters. So there we have it. The horizontal range is 50.1 meters. So I'm actually going to label that in my diagram, 50.1 meters. Find the time it is in the air. So at this point, I'm not exactly sure what to do. There might be an easy shortcut to figuring this out, but I don't know. So I'm going to just do what I do anytime we have a projectile problem and start by, well, one, we have our initial velocity, but it's at an angle. So let's resolve that vector into its components, and then let's fill in our projectile motion table to solve for our other unknowns. So we have our initial velocity. It's 22.5 meters per second, which means the x component of our velocity is here, v naught x, and the y component of our initial velocity is here, v naught y. This is 40 degrees. We can use trig to solve for v naught x and v naught y. V naught x, which is just vx, because it's a constant velocity in the x direction, is going to be 22.5 times cos of 40 degrees, which is 17.2 meters per second. V naught y is going to be 22.5 meters per second sine of 40 degrees. 22.5 sine of 40, and our calculator gives us 14.5 meters per second. I'm doing 3 sig figs, and you always want to do at least 3 sig figs when you're dealing with projectile motion, because if you don't have enough sig figs, then your rounding errors can compound and compound and compound. 4 sig figs might even be better to get a more accurate answer here. But let's see. Oh, okay, so we have our initial x velocity and our initial y velocity. Let's now solve for everything else we need. Now the thing is, we can choose one of 2 points to look at when we're filling in our table for x and y. We know we have to look at the total distance to get the total time in the air, but we also need to look at half the distance to get the maximum height. So I can choose either one to figure things out. And I'm just going to look at, basically my initial point is going to be the launch point, and my final point is going to be the top, the very top up here. So we're going to do x and y, and this is x and y to get to the top. Well, delta x to get to the top is just half of the range. And as I say that, I realize I made a typo earlier on the range. It's not 50.1, it's 50.8 meters. Let me just fix that. Yeah, because of the symmetry, the horizontal distance to the maximum, or the top of the trajectory, is half of our total range. So we just do 50.8 over 2. Delta x total over 2 equals, I'm going to leave myself a little bit more room. It's going to be 25.4 meters. 25.4 meters. We know that Vx, well, we just solved for it. Our x is constant velocity motion, so this is going to be 17.2 meters per second. And t is an unknown. In the y direction, delta y is an unknown. That's the height to the top. The initial y is, well, we solved for that over here when we broke our initial velocity into components, 14.5 meters per second. The final y, well, it's at the very top of its trajectory, so all of our velocity is in the x direction. The final y, at the very top at least, is 0. Our acceleration in the y direction is negative 9.81 meters per second squared. Gravity's pulling down. And our time is an unknown. So we can use either x or y to solve for the time, and we can use either x or y to solve for, well, actually no, we can use the y direction to solve for delta y to get to the very top. So it doesn't really matter which we do first, but I'm going to just use x to find the time. Find the time. And we can use our equation in the x direction. Delta x equals velocity times time, which means time is just delta x over velocity. So that's going to be 25.4 meters divided by 17.2 meters per second, which gives us a time of 1.48 seconds. 1.48 seconds. Now keep in mind, this is the time to the top of the flight, but I'm still going to fill it into the table. 1.48 seconds. 1.48 seconds. Something we've solved for. And the last thing we need to solve for is delta y. Well, because we have everything else in the y direction, we can use any of our kinematics equations in the y direction to do it. I'm just going to do, how about delta y is equal to, how about v naught y times t plus 1/2 a t squared, which is equal to, our initial velocity is 14.5 times our time is 1.48 seconds, plus 1/2 times negative 9.81, that negative because gravity pulls down, times 1.48 squared. Our delta y ends up being 14.5 times 1.48 plus 0.5 times negative 9.81 times 1.48 squared. Delta y ends up being 10.7 meters. 10.7 meters. Let's underline that. Okay, so we filled in our entire table. Now we just have to answer the question the best we can. Hopefully we have enough information. Okay, so we need to find the time the soccer ball is in the air. And we've solved for time here, but that was the time to get to the top. But because of the symmetry, the time in the air is just equal to twice the time to get to the top. And we've already solved for the time to get to the top. It's just 1.48 seconds. So if we multiply 1.48 by 2, we get the total time of 2.96 seconds. And then we need to find, in part B, the maximum height of the soccer ball. That's going to be delta y to the top, which we just solved for. And it's 10.7 meters. And looks like we've solved for everything. We don't need to do anything else. Let me just quickly box the answer, and that's that. So the essential idea here is we can use the range equation to kind of simplify things. And if we have a situation where a projectile is launched and ends at the same height, the symmetry makes things a lot easier. And in general, I recommend when you build your table of x and y, looking at the displacement, solving for the points between your launch and your highest point. Because then you can just double things to double the time and double the displacement to get the totals. But also then you'll be able to solve for the maximum height. If you don't need the maximum height, then that doesn't matter. Anyway, I hope this was helpful. Bye.